Welcome to the Introduction to Timing Analysis. In this video, we will cover the fundamentals of timing analysis in digital logic and design. We will explore key concepts such as setup time, hold time, and propagation delay. Let's begin by discussing setup time. Setup time is the minimum amount of time that the data input must be stable before the clock edge in order for the data to be reliably sampled by the register. In the timing diagram, you can see the relationship between the clock signal and the data signal, with the setup time indicating how early the data must be stable before the clock edge. Now let's consider hold time. Hold time is the minimum amount of time that the data input must remain stable after the clock edge in order to be reliably captured by the register. Looking at the timing diagram, you can see the relationship between the clock signal and the data signal, with the hold time indicating how long the data must remain stable after the clock edge. Next, let's discuss propagation delay. Propagation delay is the time delay between a change in the input of a logic gate or circuit and the corresponding change in its output. In the diagram, you can see the input signal and the output signal, and the time difference between the change in input and the change in output represents the propagation delay, which is denoted as TPD. Now let's delve into setup time analysis. The equation to analyze setup time is T clock must be greater than or equal to T propagation delay plus T setup, where T clock is the clock period, T propagation delay is the propagation delay, and T setup is the setup time. Here is a simple Python code that checks for setup time violations. Define a function named check_setup that takes T clock, TPD, and T setup as parameters. If T clock is greater than or equal to TPD plus T setup, it returns valid, else it returns violation. For example, if T clock is 10, TPD is 5, and T setup is 2, the function returns valid. Now let's delve into hold time analysis. The analysis equation is T propagation delay must be greater than or equal to T hold, where T propagation delay is the propagation delay, and T hold is the hold time. The data must remain stable after the clock edge to meet this condition. Here's a Python code example to check for hold time violations. Define a function named check_hold that takes TPD and T hold as parameters. If TPD is greater than or equal to T hold, it returns valid, else it returns violation. For example, if TPD is 3 and T hold is 1, the function returns valid. Now let's talk about critical path analysis. The critical path is the longest combinational logic path between sequential elements, which determines the maximum operating frequency of the circuit. The equation for maximum frequency is T clock minimum equals T propagation delay maximum plus T setup. And Fmax equals 1 divided by T clock minimum. In summary, we've covered several key concepts. Setup time, where T clock must be greater than or equal to T propagation delay plus T setup, ensures that data is stable before the clock edge. Hold time, where T propagation delay must be greater than or equal to T hold, ensures that data is stable after the clock edge. Propagation delay is the signal transmission delay, calculated as T out minus T in. Maximum frequency is limited by the critical path and is equal to 1 divided by T clock minimum. Proper timing analysis ensures reliable digital system operation. High voltage. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.